Okay, we're going to finish off this unit studying capacitors in circuits. And if you remember, a capacitor is a device that stores charge, and the simplest form of capacitor is two parallel plates. So when I draw them in a circuit, it might look like this. I have my battery, and connected to the battery is a pair of parallel plates, and that's how you draw a capacitor in a circuit. Now there's one thing you're going to notice. This capacitor has a gap in it. It's an opening. So we're going to make note that a capacitor is open. So once charged, once they're charged, the current stops. And that happens very quickly, because what happens is, initially, some charge will leak off. The negatives want to get away from the negative side of this battery. So the electrons are going to start to flow through here, and they're going to start to pile up on this bottom plate. So this bottom plate is going to be negatively charged. But very rapidly, the negatives don't want to flow out of here anymore because this plate is negative, so they're not attracted to that plate anymore. So the current will stop. At the same time, the negatives in here get attracted to the positive end and flow this way. So this ends up with a positive charge. And as soon as it's charged, the current is going to stop. Now to find the amount of charge, we can use this equation, which we had in our static electricity unit. Q equals C times V. That's going to be like our V equals IR for capacitors. Now we need to differentiate between parallel circuits with capacitors in them and series circuits with capacitors in them. For our parallel, it's going to look like this. We'll have our battery, and we will connect it to two capacitors, or it could be 3 or 4, but they're going to be in parallel with each other like this. And the rules are going to be very similar to the parallel rules for resistors. If I look at my loop rule, that's going to tell me whatever voltage I gain in the battery, I have to lose by the time I get back. So if I look at the left-hand loop, I'm going to gain a certain voltage here, and I'm going to lose it by the time I get back. Well, I only went through this one capacitor, so the voltage for that capacitor has to be the same as the total. Same thing if I do the outside loop. The voltage for this capacitor is going to be the same as for the battery. So V total is going to equal V1 equals V2, and that's the same as the voltage rule for parallel. The charge rule is going to look like this, Q total. Whatever charge leaks off of this negative side, some of it's going to get deposited on this first capacitor, and some of it's going to get deposited on second capacitor. So those two are going to add up to the total. Oops. So Q total equals Q1 plus Q2. And then our last rule is going to be the capacitance rule, and C total is going to equal C1 plus CT. It's the ability to, remember, capacitance is the ability to store charge, and if I have them hooked up like this, I can store charge on both of these. So I'm increasing the amount of charge I can store, I'm increasing the capacitance. So in parallel for resistors, it was the reciprocal rule, but for capacitors, you just add them up. Now for our series, it's going to look something like this. Here's my battery, and I'm going to connect that to, say, 2 capacitors. And if I think of my loop rule, V total is going to equal V1 plus V2. Just like for resistors, whatever I gain through this battery, I have to lose when I get back. So if I gain 10 here, and I lost 4 through this one, I'd have to lose the other 6 through this one. So these two add to that. my charge is the same. Whatever electrons get pushed through here and get deposited on this are replaced by electrons coming off of here. So the charge on this plate is going to be the same as the charge on the top plate. So it's just like in series for resistors, the current was constant because there was only one loop. Same thing. The charge is going to be the same. And the rule for capacitance in series is the reciprocal rule. So they're very, very similar to resistors. The only difference is the capacitance rules switch. It was reciprocal for parallel for resistors. For series, or for capacitors, it's reciprocal for series. Now our first example is just going to be a parallel. And I'm going to change these numbers just because they're very awkward. Having 200 nanofarads, we're running around with it 200 times 10 to the ninth. I'm just going to change this to 2 and change this to 8. And that's going to make our lives a whole lot easier. So I'm going to treat it like I was doing resistors. When I have resistors in parallel, I do a chart. I'm going to do the same thing, except on this side, I'm going to have Q, V, and C, and total 1 and 2, because our rule is not V equals IR, it's Q equals C times V. So there's my chart. I'll put in my givens. The 100 volts is going to go here. I sometimes make a mistake and put the voltage up here because in our other chart voltage is on the top. So you just have to be careful. And our capacitance are going to be 2 and 8. Now this is going to be a pretty simple example. When I look at my parallel rules, I can see a couple things that are going to be really easy to deal with. First off, the voltages are all the same. So I know this voltage is going to be 100, and I know this voltage is going to be 100. And then our capacitances add. So C1 plus C2 is going to be the total. 2 plus 8 is just going to give me a total of 10. Then, if you remember, it's Q equals CV. So I'm going to multiply 10 times 100 and get 1,000. 2 times 100 is 200. And 8 times 100 is 800. And our little check is, up here it tells us that Q total should equal Q1 plus Q2. And it does. 1,000 equals 200 plus 800. Our second example is a little bit more complicated. And again, I'm going to try to simplify the numbers a little bit. I'm just going to make this one 2. I'm going to make this one 4. And I'm going to make this one 8. And make up my chart. Down this side, I'm going to have Q, V, C. And across the top, I'm going to have total 1, 2, and 3. So like so. And across this way. Now my capacitances are 2, 4, and 8. And then my voltage is 120 volts. Now, I'm going to look at this parallel part here first. I have a 2 and 8 in parallel with each other, and then that combination is in series with the 4. So I'm going to figure out the parallel part, and all I do is add them for parallel capacitances. So it's going to be 8 plus 2 gives me a total of 10 for this part. So this is equivalent to a 10. Now that 10 is in series with the 4. So to get the total, I have to use the series rule, which for capacitors is the reciprocal. So 1 over 10 plus 1 over 4. My common denominator is 20. So that's going to give me 2 over 20 plus 5 over 20 gives me 7 over 20. That's the reciprocal of the capacitance. So to get the capacitance, I have to take the reciprocal. It is 20 over 7. When I do that, I get a value of 2.86. So here I get 2.86. Now, the next thing is going to be to find Q total. I'll do Q equals CV. So Q equals CV. So Q equals 2.86 times 120. And that's going to give me a value of 343 for the charge that came out of the battery. Now my next step is either going to be to figure out what one of the voltages is or one of the charges. Now I can't do the voltage because any loop I take, I gain 120 through the battery, I have to lose 120 by the time I get back. But any loop I take, if I go to the left branch here, I'm going to lose some of the 120 there and some more of it there. So I know those two are going to add to 120 volts, but I don't know what either one is. However, for the charge, I can think of this. Whatever charge comes out of the positive side of the battery, say here, is going to get deposited on this 4. So the Q for the battery, the Q total, has to equal the Q for the 4. So here's my 4. I know it has to have a charge of 343. Then I can use that to find this voltage. So I'll do Q equals CV again. So Q equals CV, and that gives me 343 equals 4V, and I get a voltage of about 85.7. So I'll put that in here, 85.7. Now, if you remember, I just said that the voltage here plus the voltage here has to add up to 120 because I gain 120 there, I lose 85.7 up there, and then I lose the rest of it over here. So this voltage is going to be 120. So we'll write it down this way. V1 is going to be 120 minus 85.7, and that's going to give me a value of 34.3. So I'm going to put that in here, 34.3. And it's going to be the same for this one over here, because these are in parallel, and in parallel they have to be the same. And then I can finish it up just by multiplying C times V to get Q. So 2 times 34.3 is going to give me roughly 69 if I'm rounding. And 8 times 34.3 is going to give me roughly 274. Now I can check this. Whatever charge is on this plate gets split over these two. So this Q here, the 343, should equal these two added together. And if I do that, 274 plus 69, I should get 343. So it does check out.